Welcome to CE 402 Environmental Engineering 2 Module 3 Part 2. In this session, I am going to discuss about the oxygen sag analysis. It is actually the dissolved oxygen curve in the dilution water. The oxygen sag or oxygen deficit in the stream at any point of time during self-purification process is the difference between the saturation dissolved oxygen content and the actual dissolved oxygen content at that time. When the wastewater is disposed of into the stream or river, the dissolved oxygen content will get reduced in the dilution water. This analysis is to be done to analyze the condition, that is the pollution status of the dilution water or the disposing water. So that is the surface water, that may be a static water body or a moving water body like a river or stream. This can be calculated by getting the data, that is the actual dissolved oxygen content in the dilution water and the saturation dissolved oxygen content of that dilution water. This is the equation. Second point is the equation for the oxygen deficit, that is D is equal to saturation DO minus actual DU. This is the oxygen sag curve. That is, in y-axis, the oxygen concentration, and in the x-axis, the downstream distance. That is the distance traveled by the wastewater through the dilution water, that is the river or stream. Here you can see a straight line parallel to the x-axis, that is the saturation concentration of dissolved oxygen content in the river or stream. You can see the actual dissolved oxygen curve, that is sag curve. In the y-axis, you can see the point where it is considered as the mixing point or the point of disposal, where the dissolved oxygen content is less than that of saturation concentration. And in the first zone, that is our preliminary zone, the dissolved oxygen content will get reduced due to the pollution in the wastewater, and then a minimum dissolved oxygen content will be reached due to the decomposition of organic matter in the wastewater. And after the maximum decomposition using the dissolved oxygen content in the stream, the dissolved oxygen will get increased due to the re-aeration happening in the dilution water, that is river or stream, and the re-aeration happens and the dissolved oxygen content will get increased and it will reach up to the level of saturation concentration when the wastewater travels from the point of disposal to a certain distance where the water flows. This is the oxygen sag curve, and the dotted line shown in the curve is in the graph is the BOD curve. At the disposal point, the biochemical oxygen demand will be very high, and this BOD content utilizes the dissolved oxygen content in the dilution water, and the BOD content will get reduced and it will be minimum at a distance far from the point of disposal. This is the oxygen sag curve. And then this graph shows the deoxygenation curve, reoxygenation curve, and the oxygen sag curve. Here you can see the first point, that is at the point of disposal, a saturation DO graph is shown, that is parallel to the x-axis, and at the point of disposal, the dissolved oxygen content will get reduced, that is the point D0, that is the dissolved oxygen content or oxygen deficit at the point of disposal. And traveling at a distance, the oxygen deficit will be dt at a time t. Here the y-axis is the time of flow in stream, that is t in days, and in y-axis you can see it is the dissolved oxygen content percentage. And you can see the oxygen sag curve that we already discussed in the previous graph. And here two graphs extra introduced, that is the reoxygenation curve and the deoxygenation curve. Deoxygenation curve means the oxygen utilizing curve. That is, the dissolved oxygen content will get utilized due to the presence of pollution in the wastewater. You can see the deoxygenation curve at a point DO, that is the initial oxygen deficit. The dissolved oxygen content will get reduced, and it will that is the deoxygenation, that is the oxygen content will reduced, and it will move parallel to the x-axis. And you can see the reoxygenation curve. In the reoxygenation curve, the dissolved oxygen content will be very less compared in the initial stages, and after traveling a long distance and after traveling at a time t, the reoxygenation, that is the oxygen again mixes again with the this dilution water and enters into the water, and the dissolved oxygen content in the dilution water will get increased due to the reoxygenation. This is mainly happens due to the re-aeration of the dilution water. This dotted line shows the reoxygenation curve, and the combination of deoxygenation curve and reoxygenation curves gives the oxygen sag curve. Then the explanation of deoxygenation curve I already explained. Then the reoxygenation curve. Then the oxygen sag curve. Oxygen sag curve or oxygen deficit curve. The oxygen deficit, as I already explained in the previous slide, that is D is equal to saturation DO minus the actual DO. And the Streeter-Phelps equation can be used for the analysis of oxygen sag curve. This Streeter-Phelps equation is the mathematical analysis of oxygen sag curve. The analysis of oxygen sag curve can be easily done by superimposing the rates of deoxygenation and reoxygenation as suggested by Streeter-Phelps analysis. The rate of change in the dissolved oxygen deficit is the sum of the two reactions as explained below. This is the normal derivation of our Streeter-Phelps equation, that is deoxygenation and reoxygenation as a combination. dt is the dissolved oxygen deficit, and Lt is the amount of first stage BOD remaining at any time t, and K dash as the BOD reaction rate constant or deoxygenation curve, deoxygenation constant. It is generally expressed as Kd, and R dash is the reoxygenation constant. Generally, it is expressed as Kr, and you can see the equation as the equation number 4 and 5, and I will explain this equation in relation with the problem related to oxygen deficit. And K is the BOD reaction rate constant to the base 10, and R or Kr is the reoxygenation constant to the base 10. D0 is the initial oxygen deficit at the point of disposal, and T is the time of travel in the stream from the point of discharge. That is x by u, and x is the distance along the stream and u is the stream velocity. This is the Streeter-Phelps oxygen sag equation, and the graphical representation of the equation is shown in figure. This is same as that of oxygen sag curve I already explained in the first graph. I think you understood this oxygen sag curve, and this is very important. And this is the frequently asked question in the university examinations. So please go through the session once again and understand the concept of oxygen sag curve and Strater-Phelps equation. The Strater-Phelps equation will be explained in the problem related to this oxygen deficit. Thank you for listening. See you in the next class.